everybody, and welcome to Washington, D.C. We're here on the National Mall to celebrate the big Earth Day celebration going on all weekend here on the mall. My name is Steve Cole from NASA's Office of Communications, and we have 5 Earth scientists from NASA here to talk to you about how Earth is changing, how we see it from space, and a lot of the new technology that we've been using to keep an eye on Earth and how it's doing. We're being broadcast on NASA TV, online, on Ustream. We're going to take questions from the audience after each speaker, and also online through the chat at Ustream. So our moderator for today for all the talks is Tom Wagner from NASA headquarters. Tom?
Hey, welcome to the NASA Green Theater on the National Mall. My name is Tom Wagner. I'm the cryosphere program scientist at NASA headquarters, which means I'm in charge of studying the ice and sea level rise and change at the Earth's poles. And what we've got for you today is we've got 4 of our top Earth scientists are here to tell you about the status of the Earth from space, the kinds of latest scientific results that we're seeing about the Earth, to give us kind of a checkup and report. And so what we're going to do is we're going to have the speakers come up and talk for about 10 minutes, and then we're going to take questions live from you guys here in the audience and also online. So all you kids out there, when you're listening to talk, think of things that you want to ask them. Now, our first speaker is going to tell us about the human fingerprint of what we see from space. His name is Dr. Piers Sellers, and he's also a NASA astronaut. So come on up, Piers, and take it away.
Hi, everybody. Is this working? Great. Okay. So how's everybody doing? Good. Anyone here want to go into space? Yeah. Anyone see the shuttle when it was flying around Washington? Yeah? Okay. I actually rode that thing into orbit, which is very nice. Nice ride. You get tremendous view looking down the world. And then you can jump out of your spaceship in a little white spacesuit and look down. And at night, you can really tell that there are people down there. And the way you can tell is because the Earth kind of looks like this. Now, this is made up of a whole lot of photos taken on the night side from satellites, and you can really tell where the people are. You can tell where 7 billion people, that's all of you lot, including me, where 7 billion people are living and working and doing stuff. And you can tell where they're doing it. So if you look carefully, you can see that really densely populated areas like the East Coast and Europe, tons and tons of people, lots of city lights, all kinds of people, and then big chunks of the world, like the middle of the Amazon basin, which my friend is going to talk about in a minute, deserts of Africa, and the middle of Australia, very lonely places. Now, one thing here, this is very helpful. If you want to rent a house somewhere in the world, the bits with lots of lights are really expensive. This is just so you know. You look, here's New York, London, Tokyo, they're really bright, and the rents are sky high. And I've been up to this place here. This is actually an Inuit settlement, and one light bulb is bravely glowing there, and I got a really cheap bed for the night. Good to know. Okay, the other things that's really interesting to note. Yeah? Okay, can you hear me in the back? I'll wave my arms. All right. The other thing is that lots of people live around the coasts. All around the world. Lots of people like to live around the coasts. That's where the cities are, that do trade, ship things in and out, and all the rest of it. And with sea level rise, that could be a little bit of a problem. So keep your eye on that. Other things that you can see from space. This is a man-made island that is being built off Dubai. It's kind of tourist resort and all the rest of it, some luxury homes. And you can see this actually out of your window from a space shuttle. And they've been building it steadily, and now this is what it looks like a big palm tree. Quite amazing. So people are actually changing the landscape that you can see with your naked eye from orbit. And the last thing I can show you here is some of the impacts that people have on the environment that are not so good. This is mountaintop mining in West Virginia, I think. And what you can see is the technique here is you just shave off the top of the mountain to get at the coal. And you can see what it does to the landscape over time. Makes quite a mess because the trees don't grow back very quickly, the rain hits it, and all this stuff washes off. So you can see a lot from up there. You can see what everybody's doing. 7 billion people now, moving up to about 9.5 billion during my lifetime, and then probably coming down slowly. But all of them busy, and all of them with the lights on. Any questions? Anybody wants to know what it's like to fly in space? Very exciting, let me tell you. The launch really gets your attention. Okay.
Hey, Pierce, I got a question.
Yeah.
So now, you've had this amazing career being a climate change scientist, then also being an astronaut, now coming back and being a climate change scientist. So when you were a kid like these guys back in school, you probably had no idea, but what is it that made you go and study those hard subjects like math and physics and stuff like that to get to, so you could do all this?
That's a really good question. Two things made me do it. One was that when I was a little kid, the Americans, which is where I am now, the Americans were preparing to land on the moon. And I saw that all on my little black and white TV in London, and I thought it was the best thing since sliced bread. This was the most exciting thing that ever happened. And you know, the space exploration is something of our lifetime. It's something of our generation, and I still find it exciting. And the other thing was I had great teachers that got me really interested in how beautiful physics, biology, mathematics is. You know, after a while, I really appreciated how beautiful it is and all the cool things you can do and all the really interesting jobs you can do. All the scientists around here, by the way, they work all the time. Do you know why they work all the time? Because their jobs are really cool. It's fun. It's a lot of fun. It beats the heck out of most jobs. So I'd encourage all your kids, if you want an interesting life where you enjoy your work and do good, science. Much better than Latin, which I found very, very hard. Yeah.
Any questions from out here? Steve, any questions from online? Hey, one other one then. Can you tell us a little bit, I mean, since you've been in space and been in orbit, can you tell us a little bit how an image like this is made? I mean, that one over there, that's the whole planet, but a satellite doesn't see the whole planet all at once, does it?
No, it doesn't. The satellite basically is like a lawnmower. It goes around the world like this, taking long, thin stripes of data. And then afterwards, we use computers and people to sort of match up all these stripes of data. We get rid of the clouds by coming back if it's cloudy one day, we come back another day when it's not cloudy. So what you're looking at is a carefully selected set of views, cloud-free, perfect viewing conditions. Takes about a year to build this up, all stitched together. And you can't see the lines in between because we do a very careful job of matching it up. But this is made up of, I think, about, you know, dozens and dozens of different images. Yeah. Yeah, somebody had a question. Yes,
Sure, we
sir.
got a question right there, the
guy
young
with
man in the
Brazil
yellow
t-shirt.
shirt.
Yeah. When's the next person going to space?
Where?
Right. Where? Well, we think, we hope, that in about 20 years, we're going to be sending people to Mars, to go around Mars, okay? Which would be very exciting, because that's a long way away, and Mars is a planet that's really interesting. I would like to go, but I'm probably a bit old.
It has lots of dust.
What's that?
Lots of dust.
Lots of dust.
Lots of dust there, yeah, we need...
Hey,
maybe
Ronnie, there's a
take
question
vacuum
right there.
cleaner. Yeah.
I just want to know how long does it take from Earth to Mars?
How long would it take to get to Mars? Right now, we think it'd take about 200 days to get out there. And if you just went to orbit around there, you'd probably spend about 2 months there, then 200 days to get back. If you wanted to land on there and run around, it'd be 200 days out, 500 days there, 200 back. So it'd be best part of 3 years. But the tax advantage is huge. So you have to bear that in mind.
All right, one more question, red shirt in the back.
Can you elaborate on your comment earlier that expectation is that Earth population will go up to 8 or 9 million and then, or 8 or 9 billion, and then start to come down at that point?
That's what all the models and indications are telling us. We're finding out that as more and more people are getting educated and literate, then the families are getting smaller around the world. And we've seen that all over the world. So we just bounced through 7 billion a few months ago. And the models tell us that it looks like it's going to top out somewhere around about 9.5 billion and then gradually ramp down slowly, which is better than the 12 billion that everyone thought it was going to be when I was a kid, you know, so less impact.
All right. Hey, Pierce, thank you very
Thank
much. I
you.
might switch microphones with it. Hey, so our next speaker is Dr. Compton Tucker, who's going to give us a checkup on the health of the world's forests and tell us how we study those from space. And one of the amazing things is not only has he studied them from space, he's also spent a lot of time walking around in the jungles themselves, and he may tell us some of those stories. Jim, take it away.
Okay, thanks, Tom. One of the really cool things about working for NASA and using satellite data to study the Earth is you have to do field work to understand what you're seeing. You can't just look at things from a distance and say, well, we see this or we see that. but you have to go there in person and do field work in controlled settings. I study tropical forests, and I use satellite data for that. And on the left-hand side, we see some strips of satellite data from one day in the 1970s. Here we have something from 1984, 1992, 2001, and 2010. And the scale you're looking at, this is about 500 miles from top to bottom for each of these strips. And the bottom distance is about 110 miles, or about the distance from Washington, D.C. to Philadelphia. So you can use satellite data to study forests. Now this is a false color image looking down. If we were in space, or we were in the space shuttle and looking down, these areas that are bright red would look bright green. But we use some wavelengths which our eyes can't see, and we have to then represent those in colors. So we would never see an image like this. But all of these red areas are where we have tropical forests. This is an area where I have worked extensively. I've worked in this area, which is close to Santa Cruz, Bolivia. I've been all up through here. I've spent a lot of time in a national park here, and I've also worked up here on the border where every weekend or every other week we would go to get supplies and buy beer and do it on Saturday because that was bingo night in a town called Pimenteira in Brazil. And we always wanted to enter and would enter the bingo contest because the first prize we weren't interested in. That was 2 frozen chickens. But the second prize was a case of a Brazilian beer called Antarctica beer, which you serve at about 33 degrees Fahrenheit. Anyway, so we always hoped to win second prize. And if we won the first prize, we would try and give it away because that was 2 frozen chickens. Anyway, so in the 1970s, when we had our first Earth Day, there was almost no disturbance of all of these red colors. And then you see more of these blue colors come in these patterns. And this is because there was tropical forest clearing into agriculture and ranches. So here we have a little bit of clearing in Brazil. Here we have more. And now we have a lot in 2001 and 2010. And then also on the southern end in Bolivia, there was almost no expansion of agriculture into this area. And then we see it starts to expand. There are a few roads. There are some features here. And once again, this is the distance from Washington, D.C. to Philadelphia, about 110 nautical miles. Then there's more, and then all of a sudden, bang, the whole area goes. But this actually is a good area to have agricultural development because the soils in this area are very, very good, whereas in tropical forest, because it rains so much, you tend to have bad soils up in here. And so most of this area is still in tropical forest. It's a really cool place to go. I've had several expeditions there, and when you do work in tropical forest, you try and cover up as much of your body as you can because, like today, you perspire. And when you sweat, you tend to attract bees and wasps because they want to get salt in your perspiration. And you're sort of like a walking salt lick. So every day you have to bathe in rivers and wash your clothes out and also wash yourself, or else it's worse the saltier you are. And what bees and wasps do, they're social insects, and we all know about science, technology, engineering, and math. And these are really excellent areas to study if you're interested in science, and there are many cool things to do. So the bees and wasps, being social insects, then communicate where you are, where all this salt is, and it's on you and your clothes. So the first day you might have 10 bees or wasps, the next day 100, the next day 1,000, and then, I'm not exaggerating, in the morning when you wake up after several days at a camp in the Amazon, you can hear, as soon as the sun comes up, this sort of dull zzz, and it's the bees and wasps coming. They're not trying to bite you, but they're just after the salt. Okay, so what I've found, and my coworkers, is in tropical forests, in the Amazon, about 15% of the Amazon has been deforested, and about 80 or 85% still remains. And that's important because tropical forests have the greatest biological diversity, or the greatest number of plants, animals, and also microbes, bacteria, and viruses. On one expedition in this area with one of my coworkers, he came down with hantavirus. He was unconscious for 2 or 3 weeks, but when he was unconscious, he stopped smoking. And then he recovered, and he has no recollection of going through smoker's withdrawal when you try and stop smoking. That's the only good thing about that. But it's unusual when bad things happen. And so what these images show is how we are transforming tropical forests here in Brazil, here in Bolivia, going from when we had the first Earth Day in the 1970s all the way through to just 2 years ago. There is a national park which you can visit right in here called Noel Kemp National Park. It's a really cool place. I've been there 10 or 15 times. There are very, very few people who visit it every year, maybe 4,000 or 5,000. It's a great place to see river otters, to see jaguars, to see monkeys, to see wild pigs or peccaries, and lots of really cool and colorful birds. So I'll stop there, and the reason that I got into this was I was working in a bank after I got my bachelor's degree in biology, and I didn't like that bank, so I went to another bank. That was also really boring. And so then I said, banking is not for me. I've got to go back to graduate school, and so I did. And then when I finished graduate school, I came to NASA, and I've been there ever since. And it's really, really cool work because of my background in science and math. So I'll stop there and answer any questions from the audience. Anything about tropical forests, dangerous animals, bees or wasps? I have a lot of first-person singular experience. Yes.
How many animals would you say are endangered? Or how many types of species of animals are endangered? Would you?
Well, there are quite a few endangered animals, and where they are endangered are where you have the destruction of habitat. So even though I study tropical forests, I'm very interested in identifying areas which where the forest is replaced with agricultural fields, and then a biologist can use that information to see what animals there and plants are being endangered. So that's a big part of what I do, is give this information to people I work with who are biologists who study different types of animals, perhaps butterflies, perhaps jaguars, or plants, to tell where they should focus their studies and identify those animals at risk.
Question right here.
Well, okay, how do we get there? Well, as you can see, there aren't too many roads in this area. There's one road that goes up like this, and we have to do a lot of hiking. We also sometimes on rivers go in boats that are called peke boats. These are long dugout canoes with an industrial sort of lawnmower engine with a long propeller out the back, and the engine sounds like peke. And so you go down the rivers in boats like this because your first choice is to go on a road. There aren't many roads. So our next choice is by peke boats. And the third choice, you have to either make a trail and hike or find an existing trail and hike. So if you like hiking, if you like camping, it's a great way to see some really, really cool places and to encounter some really cool animals.
Hey, we got a couple of questions from online for Steve over here.
Yeah, these are questions we had from Ustream. Can NASA's high-resolution pictures from space see a person walking on the ground?
Well, we use commercial satellite data where you can see people walking on the ground by the shadows they cast. If you're looking straight down, unless you were incredibly large, like a hippopotamus, you probably couldn't see you, but you can see their shadow if the sun isn't directly overhead. So yes, by their shadows is the answer.
Okay, another different question about deforestation. Is NASA doing research in countries like India and China about deforestation?
Yes, we're doing research on the whole planet, and this information is available to everyone. There are no restrictions on our data. And anyone can get them. And so some of my coworkers are studying forests in China, forests in India, although I primarily work on tropical forests in South America and the Amazon basin, and also in equatorial Africa and Madagascar. But the answer to that is yes.
Do you have another one? Hey, Jim, a question for you. You've also worked on things like diseases and how we can actually use satellite data like this to figure out where a disease would go. Could you tell us a little bit about that?
Sure. One of the cool things about using satellite data is you have these every day for the entire planet, day after day. And now we have satellite data for almost 31 years. And by looking at certain conditions for some diseases that are climatically or ecologically coupled, you can then correlate and associate those data and how they vary in time with disease outbreaks. So some coworkers of mine and I started in 1985 working on a disease called Rift Valley fever. It's from, as the name suggests, from the Rift Valley of Africa. It's a hemorrhagic fever transmitted by mosquitoes, and it occurs in where you have arid and semi-arid vegetation, and the satellite data show when it's rained and how persistent the rainfall is. And if that persists for more than 8 weeks, that's an excellent suggestion where you will have Rift Valley fever outbreaks. We'll publish numerous papers on the biology and on using these data for Rift Valley fever, and we can do this with an accuracy of about 60%, 2 months in advance of the outbreak, which then enables control measures to be implemented. And this is one of the major things that I've worked on that I'm really, really proud of, but it's only because we approached this in a systematic way and had satellite data for 30 years now. And so today we're processing data from yesterday, and we have more information and are doing this very close to real time.
Hey, so one other one too. When you were kind of in on the ground floor of this stuff back in the 70s and 80s, what was it like when you first started out? I mean, did people believe that you were going to be able to map forests from space and even do these kind of high-tech things you're doing now, like figure out where a disease might go?
The simple answer is no. I had a lot of people who told me what you're doing is really stupid. It won't work. I don't know why you're trying to use satellites. This hasn't been done before. You shouldn't even try it. So I didn't believe them. I thought they were crazy. And I said, let's at least look and see. Let's experiment, because I really like problems and experimentation. And so we started some programs. We had no idea if they would work or not. They have turned out to be wildly successful, and now one of them is the most commonly used technique to study vegetation from space, and it's where you use data from weather satellites day after day after day, and so now we have almost 31 years of data, which we summarize into data every 2 weeks, and this is extremely useful. But the simple answer is several people told me we were stupid to do this, it wouldn't work, and besides, why do you want to do this from space when you can go out places and do it on the ground? Well, these images show there are no roads here, and in some places you have to do things from space. It's also a good way to check on other countries and see what they're doing, see if they're complying with treaty requirements. So as John McCain said, we need to see if some countries are cheating.
Hey, we got another question from online.
Yeah, one question from Ustream. How are the forests in America?
Well, I've also published papers on that, and I got into a bit of a battle royale with some people in the Pacific Northwest 20 years ago. So in the Pacific Northwest, where you have these late successional coniferous forests from Northern California up through Oregon and Washington, and then they continue into British Columbia, there only about 10% of the original old-growth forests remain. Almost all of those are in national parks or national forests. And it's also an area where you have a lot of tree farms, because trees like to grow where it's wet, warm, and flat. And so that's a very good place to have tree farms. And they're in a rotation where you grow a forest perhaps for 50 or 60 years, then it's harvested, and then they replant. So that is a very good type of forestry, because you have trees which replace what you cut down, and all the time as trees grow, they absorb carbon dioxide from the atmosphere and incorporate it into wood, so it's a major carbon sink.
Hey, one last one, Jim. So we've got all, oh, I see a question right there in the front.
How long do you stay there?
Well, sometimes you get stuck places and you have to stay a long time. One time we had to stay someplace for about a month, but usually it's maybe 3 or 4 weeks. And believe me, by the time as you get towards the end of your expedition in tropical forests, you're really happy to leave, but sometimes it may take 5 or 6 days to get out. And some of the places I've worked in this area, what you do, there are abandoned airstrips when there were drug labs in the area. Now, our Drug Enforcement Administration has driven all of the drug labs out of these areas because they would have a drug lab in tropical forests. And you wouldn't want to go there when the narco people were there, because they're very, very ruthless. But anyway, they would have a landing strip to fly the refined cocaine out. And so we would have planes fly us in after our Drug Enforcement Administration ran them all off, fly into their airstrips, drop us off, and then say, okay, we're going to come back in 3 weeks, and then we would do field work by hiking from around there. Yeah. If there was bad weather, one time we had to stay an extra week. So it all depends on where you are, or sometimes you could be someplace and the rainy season will start and the rivers will come up, and you have to wait for the rivers to go down so you can get in your peke boat and leave. So it all depends, but usually anywhere from 2 to 4 weeks.
All right. Hey, thank you very much, Jim. That was really great. I want to introduce our next speaker. Hey, our next speaker is Dr. Chris Schumann, Chris has spent a lot of time in the Earth's polar regions, studying them, being out on the ground with a shovel and digging pits, all the way through to using data from space to understand them. And he's going to tell us what's going on at the top of the planet. Chris?
Thanks, Tom. My name's Chris Schumann. My first trip to the poles began in Greenland in 1992 as a postdoc for Penn State University. There, I was working at the GISP-2 deep core site, kind of the ultimate climate data record. This is an ice core through the entire center of the Greenland ice sheet, going down almost more than 3,000 meters, going back in time more than 100,000 years. And you can tell that by looking at the record in the layers of snow and ice that are preserved in the ice sheet. My job was to try to calibrate the thermometer from the ice core to the modern observational record. Now, when I was there in 1992, the first automatic weather station was only put up in 1987, so we only had about 5 years of overlap with the modern record. So what I did was I went back in time using a series of satellites, beginning with the Nimbus series, a NASA sensor called SMMR, the Scanning Multi-Channel Microwave Radiometer. That provides a proxy for temperature through time. That begins in late 1978 and has continued through a whole series of satellites all the way through today with another sensor that NASA is flying called AMSR. That has enabled us to measure very consistently certain aspects of the Arctic and the Antarctic, including the sea ice cover, the frozen sea surface of the Arctic Ocean. You see that here, illustrated by the 2011 sea ice minimum. That's from microwave data being gathered multiple times per day, each time the satellite goes around. It's really amazing. The satellites actually go around the whole Earth in about 97 minutes. That's a pretty typical time. That's real fast. So basically, the white area shows the September sea ice cover compared to the long-term median sea ice cover, going back over that 1978 through today time period. And that's one of the ways that we know how the Arctic is changing. And we can see that both from the sea ice minimum over time. It looks a little bit like this plot over here, this climate data record. This is actually the decline in multi-year ice. Ice that forms in 1 year and lasts through multiple years. It doesn't melt away when the sun comes up in the Arctic, when the sea ice starts to retreat back. So basically, it's our eyes in the sky starting in the 70s that have enabled us to start assembling these time series that illustrate the changes that the whole Earth is going through, especially the Arctic. I'm just one research scientist at NASA. There's a whole bunch of us that are working on the cryosphere, the Arctic and the Antarctic. A bunch of our folks right now are flying on aircraft missions out of Iceland and Thule Air Force Base in northwestern Greenland. They're gathering additional data to complement the pictures that we're gathering from the satellites. Okay? So that's one of the ways that we're trying to put the whole story together of how the ice is changing. Now, being a glaciologist, it means I've seen the history of the changes in the Earth's ice cover. Those of you that have been to Central Park, there's bedrock that's polished there. So 18,000 years ago, the ice was much farther south, pushing up Long Island, carving out the Finger Lakes, making the Great Lakes wider and deeper. And that's part of the story of change. What we're seeing, though, is accelerated change in recent decades, where sea ice cover has really started to fall off, both in area and in thickness. The multi-year ice tends to be thicker, and since the big sea ice minimum in 2007, we've actually seen a substantial decrease in the overall thickness. My colleague, Sinead Farrell, has got some papers out that really show the changes in thickness over time using the ICESat time series, 2003 through 2009. We're actually going forward to launch a new version of ICESat by 2017 that'll try to continue those measurements. The aircraft missions, Operation Icebridge, flying out of Thule, flying out of Iceland, are hoping to continue some of those measurements until the next satellite goes up. What is happening, though, is as more and more of the Arctic Ocean is becoming exposed, the sea ice cover is disappearing, the albedo changes, and that water, dark water, absorbs more of the solar energy during the Arctic summer. And that ocean water is warming. And that's contributing to the overall decrease in area and thickness of the sea ice cover. It's also contributing in part to the retreat of some of the major outlet glaciers around Greenland, where that warm water can creep up underneath the ice. The floating ice starts to break up, turns into icebergs, and drifts down the fjord. And so what we're seeing is not just a retreat of the ice front, but we're seeing an acceleration of the ice out of the interior of the ice sheet, out into the ocean. That's causing the thickness to drop. Measurements from ICESat have also shown that the elevation of the surface of the Greenland ice sheet is decreasing substantially in the past decade or so. So these are the kinds of stories that we're trying to get out to everybody, because the more ice that moves from the interior of the ice sheets, Antarctica, where I do most of my work, the Antarctic Peninsula, we see big glacial changes like this as well. One of the glaciers that I study down there has lost about 600 feet of elevation in a decade after its nearby ice shelf, the Larsen B, collapsed. These are really very substantial changes, and we're seeing them through our own eyes when we can get on the ground. We're seeing them from space when the satellites go overhead, and we're seeing them from aircraft missions. And that's the kind of science that NASA does that we hope will excite you and turn you into scientists down the road, helping us continue this story. Thank you.
Chris, you talked about Greenland. Can you tell us, Greenland's this big island, it's covered with ice. Can you tell us a little bit about it? I mean, I don't think we have a good, how thick is that ice? How does it behave? What's the connection between that and sea level?
Basically, Greenland has about 3 kilometers, 3,000 meters of ice, 10,000 feet or so.
A couple of miles thick.
Couple of miles of stored on top of the island, the bedrock beneath the ice cover. Greenland's 80-some% covered in ice, and as that ice moves, it flows out towards the ocean. The ice that's stored on the land is melting around the margins, and it's flowing into the ocean from these big outlet glaciers. And that's causing sea level to rise over time as that stored water from the ice sheet is transferred out into the global ocean.
But how does that ice flow? I mean, I picture ice as like ice cubes from my refrigerator, which are kind of brittle. How does that ice flow like that?
It's a wonderful bit of physics, actually. It depends on what the temperature of the ice is, but basically the grains of ice can slide past each other just under the pressure of the overlying ice. At the GISP-2 site where I was started in glaciology, that 3 kilometers of ice basically makes the layers really thin down at the bottom, in part because they're stretching out and they're being forced to move away from the center of the island towards the margins of Greenland and out to sea.
Hey, we got a question from online. Steve?
The question about sea level. Due to the decrease in ice cover over the poles, what regions of the Earth are already now underwater?
Well, I have always wondered how I got into glaciology when there were these marvelous careers in carbonate sedimentology in the Bahamas. As an earth scientist, you think about that and you go, how did I make the choice to wear a parka and not shower for 2 months? It's really not a logical choice when you get right down to it, when you could be swimming in the ocean every day at your research site. Okay, so some of the smaller islands around the world, I know the Bahamas are one place that we're concerned about sea level rise, but basically it's all the places that Piers showed where the populations are. The whole densely populated coastlines of the world are places where sea level rise is beginning to be measured and really impact insurance rates, among other things. Yes?
Okay, we got another question from you, Steve. What kind of cycles have you seen where new ice is being made and ice is melting back?
Well, I've worked in both Greenland and Antarctica, 7 times to Greenland, 6 times to Antarctica. The dry, high interior of Antarctica, for example, has very little accumulation. It's a polar desert, but it is accumulating a little bit every year, averaged over
Accumulating
several years.
snow, you mean?
Accumulating snow, that's right. And so up in the high interior, you might get a centimeter or 2. It's so dry that your breath turns into ice crystals, because it's just that easy for them to form at these low temperatures. And that's the kind of crystals which accumulate over time. They're basically called sometimes hoarfrost, but they're very, very fine crystals. But they build up, and that's what enables the ice to become so thick in East Antarctica, the highest part of the big polar ice sheets. Around the margins, in the Antarctic Peninsula, where I'm doing some of the work, it's still accumulating up on the high part of the peninsula, but because the ocean waters are so warm nearby, where the glaciers flow down to the water, they really are disintegrating because of all that warmth being transferred into that ice.
Question.
How long do we
You
have?
might restate the question.
Can you restate that just a little bit?
Could you give us information about the feedback loop and whether or not you think we've reached a tipping point?
I think Sinead's work actually speaks very well to that point, where she shows in the Arctic sea ice cover over the Arctic Ocean that the thickness change has accelerated dramatically since 2007, where the Arctic Ocean may be warm enough now that the thicker ice is really thinning much faster all of a sudden. So I'm not sure that the Arctic climate system can't recover, but I do know that the change has accelerated, not just in the past decade or so, but in even the past few years.
Another question from online.
Yeah, here's a question from Ustream. How will the melting ice affect ocean currents?
Well, that's actually one of the really cool things about the Arctic, is because the formation of sea ice, basically the air temperatures are so cold that the sea surface itself freezes solid. You've probably been to the beach. You think to yourself, no way. How could an ocean freeze solid? Well, it happens, and it happens really rapidly. And in doing that, it actually lets loose this cold, briny byproduct, where the frozen surface basically forces off cold, salty water that falls deep down and actually drives some of the global ocean conveyor belt. That cold water flows very deep and moves south, forcing warmer water to flow up from the equators to replace it. So sea ice is a very important part of what balances the temperatures around the world. So we actually saw some indications of how important that process is in the GISP-2 ice core record, where we saw these sudden climate shifts that probably had to do with shifts in how sea ice was forming. And they were really, well, I could talk at greater length on just the ice core itself, but it's one of the ways that we actually look back in time, not just from ground observations, but from and aircraft observations and satellite observations, but by going back through the layers which have accumulated in these big ice sheets.
Hey, Chris, one last one. Can you tell us about the different ways that we study ice from space? You talked a little bit about how we look at microwaves that come off the ground, but are there other things we have?
Well, sure. We actually have the infrared temperatures of the ice sheet surface. Here's Greenland. Basically, the infrared signals which are coming back to the satellite give us an indication of the surface temperature of the ice sheet. We can actually look at the elevation changes over time by ISAT, which was a laser altimeter, which measures the surface relative to the satellite. And we go back and we measure that again months later.
But how does that work? You say laser altimeter. What does it actually do?
It actually shoots out a pulse of laser energy. And by knowing the speed of light and where the satellite was on orbit, and knowing how long it took for that pulse of laser light to get down to the ice sheet and back up to the satellite, we determined the range to the satellite from when it sent out the pulse to when it came back. So there's a distance. And by knowing where the satellite is in orbit, when we took those measurements, we actually determined the elevation of the spot on the ground. And so ISAT-1 measured 40 times a second, about every 172 meters along each orbit track. 97 minutes, it comes around, measures again, and you build up those measurements over time, and you see the elevation changes. Cool. Big changes in the Jakobshavn Glacier drainage basin, big changes in the coast of West Antarctica and Pine Island Glacier, Thwaites Glacier, big changes in the area in the Antarctic Peninsula, which I was studying, of hundreds and hundreds of feet in a decade. Cool. By building up those altimetry measurements over time.
Great. Hey, thank you very much, Chris. Really appreciate it. Our next speaker is Ernie Hilsenrath from Goddard Space Flight Center. Ernie's had an amazing, storied 40-year career at NASA, and he's going to tell us about one of the best Earth science stories of all because it has a happy ending, the ozone hole. Ernie?
Thanks a lot, Tom. I wanted to share with you my experience in working with NASA. First, I got to ask the question, can all of you hear me?
Louder.
Okay, I'll try to speak up, although this microphone, I guess, is for our web audience only and not for you people here. So I'll try to speak up as well as I can. And if you can't hear me, please remind me by just doing this. Okay, I'll try to speak up. I joined NASA in the 1960s after being inspired by a couple of things, something called Sputnik. I don't know if any of you remember Sputnik, when the Russians put a satellite into orbit. I said, gee, I have to do something. I want to play a role in this. And then, of course, John Kennedy's famous speech about going to the moon. So I joined NASA, and what I wanted to do was study astrophysics. I wanted to study the evolution and the formation of stars and galaxies. But as it turns out, when I joined the group, I really wasn't going to look at the stars and the galaxies. I was going to look back at the Earth. And I was working on some of the early weather satellites. NASA was just beginning to develop capabilities to study the Earth's weather, using its global perspective from space to understand how the atmosphere works, and it could be, if those data could be used to improve our weather forecast. And we've come a long way in doing weather forecasting using satellite data. But what I'm going to talk to you about is, by the way, it says the whole story. NASA knows how to spell. That word means two things. We're talking about the complete story, although you can't tell the complete story, but also the Antarctic ozone hole. Some of you may be familiar with this. If you take a good look at these images here, it's really pretty spectacular when you think about it in a perspective how long it took to this data. The first image of the globe of the Earth's atmospheric ozone occurred back in the 1970s with one of these early weather satellites. And at that time, we were studying ozone not because of it was an environmental concern, but because it was a scientific curiosity, and also it was a tracer in the atmosphere. We could use it maybe to improve the weather forecast. So that was in the early 70s. In the late 70s and the 1980s, we continued with these satellite data and it was discovered that something really peculiar was happening over the Antarctic. So at first, we knew that the ozone layer was in jeopardy. It was in trouble because the chemists in the laboratory realized that gases from aerosol cans and refrigerators, once they get into the atmosphere, could become activated and destroy ozone. It was a clearly a proven phenomena that it would destroy ozone, but the appearance of the Antarctic ozone hole got the worldwide attention that something needs to be done. What we have here is pictures of global ozone focused on the Antarctic. This white spot here doesn't mean there's a part of the hole. It means that the satellite didn't cover this particular area. But this starts in October 1970, goes through October's all the way through October in 2011. And you can see there was a sudden increase in the depletion of ozone. The colors here this means high ozone, this means low ozone. So this hole in the ozone layer covers the entire Antarctic region. it only lasts for a couple of months and then it closes up. So once the world, the scientists, the policymakers, the industrial community realized that there was a problem, they put a plan into effect and how this should be done and implemented. That was to ban, through an international agreement amongst all the countries in the world, to ban chlorofluorocarbons. This was the gas that's in aerosol, used to be in aerosol cans, and used as a refrigerant, to ban them completely, because this hole could have spread. As a matter of fact, some people have done studies now where if this banning of these chlorofluorocarbons hadn't taken into place, the hole would not have recovered. Ozone would have remained depleted. The Antarctic ozone hole would have been a persistent feature, and the ozone layer in the upper atmosphere would have been twice as low as it is now, and would cause twice as much UV radiation reaching the Earth's surface, causing unprecedented amounts of problems with diseases, plant production. Cancer was one of the big concerns about extra ultraviolet radiation getting down to the ground. So this is an environmental success, that we're able to recognize a global problem and rally the world's community to come up with some legislation regulating and come up with a substitute. We don't miss refrigeration. We still have our cans, but we found a reasonable substitute for freons or chlorofluorocarbons, which destroyed the ozone layer. The ozone layer is not going to really recover to normal values until 2060. So we'll continue seeing these holes, but it's not getting any deeper, and it looks like it's slowly recovering. But it'll be 2060 before there's a real recovery. A lot of people ask me, they get confused about climate change, the ozone hole, and want to understand what the connection is. And it's a very difficult topic to discuss. It's just being uncovered now. Both ozone, which is protecting us from ultraviolet radiation from the sun, carbon dioxide, which is a greenhouse gas, they work very different ways in the atmosphere, but they're very important. Any changes in their quantity that's outside of the normal range will have effect on one or the other. As it turns out, climate change may slow down the recovery of atmospheric ozone. So it looks like that the atmospheric ozone won't recover quite as fast if climate change occurs as predicted. Ozone itself is a greenhouse gas, and because of the way ozone behaves in the atmosphere, it changes the weather patterns in the upper atmosphere, which could have an influence on how climate change occurs. So there's an indirect connection between ozone change, or climate change, and ozone depletion, and how it recovers. But it's a problem that's being dealt with at the present time. Let's see. So we continue to monitor ozone. NASA's committed to continuing. These measurements here go from 1970 to 2011. That's 40 years of data. There wasn't a single satellite that measured ozone for 40 years. This is probably the product of 5 different satellites. And one of the important things that NASA does, particularly in times of climate change, is try to put the satellite data sets together. So you have a continuous stream of data, whether it's oceans, whether it's sea levels or Antarctic ice. One of the things that we're really concentrating on doing is making sure the data are accurate, and they're accurate over time, and we have to deal with the fact that these aren't measured by the same satellites. This is 5 satellites over 40 years. There was a big effort to put this data set together to show that how things are actually changing at a very slow level. So NASA's been very successful in doing that. We have partnerships with NOAA, the National Oceanographic and Atmospheric Administration, are working together to collect these data on a continuous basis. So in addition, not only is this happening in the United States, because of ozone has been such a concern globally, there are other international space agencies in Europe and Japan, and even the Chinese have recently launched one of their weather satellites that also carry instruments to measure ozone change. So I think that tells you what I mean here by the whole story about ozone and why we have an ozone hole.
Hey, thanks, Ernie. That's great. We got a couple of questions right here in the audience.
When did the reverse in policy and that international response to the ozone problem occur, and how fast did it occur? And how fast were we able to measure that it's working?
Okay, you're talking, although it's called the Montreal Protocol. The Montreal Protocol was when the chemist convinced the world scientists and the community that indeed chlorofluorocarbons, these gases in these that we're using as a refrigerant and that happened it started in late 1970s, 1980. But the reason I can't be specific is because there were changes to the protocol. It evolved. There were amendments to the protocol. When the Antarctic ozone hole appeared, that was the final blow, or the final information. That happened in about 1984 when the ozone hole was definitely there. It happened year after year. And after that, there was regulation throughout the world and ways of dealing with emerging countries who couldn't immediately dispose of their refrigerators to come up with a substitute. So it happened, it was uncovered in the 70s. Regulation was in the early 1980s.
Hey, we got a question from online.
Yeah, quick question. At what altitude is ozone measured? What altitude is the ozone layer at?
Okay, it'll take me a minute to answer.
Go ahead.
There's two kinds of ozone. People call ozone good ozone and bad ozone. The good ozone is in the stratosphere, about 20 miles up, 30, 40 kilometers up, and that's what's shielding the Earth from ultraviolet radiation reaching the surface of the Earth. This is the concern that people have would affect the biodiversity of the planet. When ultraviolet radiation, our bodies were designed, any living organism on the planet is designed so it doesn't get this ultraviolet radiation. This ultraviolet radiation gets on Mars, which is a problem for anybody who wants to go to Mars, because there's no ozone on Mars. So there's good ozone that protects life on this planet, and that's why they're concerned about depleting ozone, life on this planet. And then there's bad ozone. It's the same ozone, but it's in the lower atmosphere, near the air we breathe, and that's pollution. And it's one of the factors. Everybody here, air quality index. It's really how much ozone is in the air. That's bad ozone. It's a strong oxidant, and it can affect your lungs. It's a factor in asthma severity. So there's good ozone protecting the life on the planet by screening out ultraviolet. There's bad ozone at the ground level caused by pollution.
All right. Hey, there was a question from somebody who left. How important is a subject like mathematics, to work like this? I think a lot of times people see something like earth science, it sounds exciting, get to go outside, but you got these basic subjects like math and chemistry and physics. How do they play into something like this?
Well, math is sort of the framework for doing anything you want to do in science. Requires you able to formulate what you're doing, I guess, on a piece of paper or on a computer. Nearly everything you do, if you have a concept of how ozone depletes the atmosphere, you have to have a model first. I mean, the scientific method is proposing a model, testing the parameters, going some measurements, and then seeing if it agrees with the theory. All this theoretical basis for the models and doing your science is based on mathematical techniques. So it's the foundation for doing science. For doing science, doing engineering, mathematics is the foundation for. You can look anywhere you want to around here. Mathematics, putting up this tent required mathematical expressions. Using this microphone required mathematics.
Hey, any other questions from the audience? All right. Hey, thank you very much, Ernie. That was great. Take that. Hey, before we close out, I just wanted to say, take us back for a minute. The first Earth Day was back in 1970. And that was right, during the Apollo program, we were first getting our pictures back of the Earth as this big blue marble up in space. But we really barely had satellites orbiting the Earth that time. And now we're finally at this point where we've got 15 satellites in orbit right now telling us all these fascinating things. And probably the most important thing we've learned from all this work is that the Earth is this great big interconnected systems. And that when we make a change in one place, it translates all the way across the world. And the other thing, too, is as we started out with the first talk, we are actually affecting things. And we're affecting things so much that we can see it. In wrapping up, does anybody have any final questions, any comments or anything? Hey, we've got one last thing from Steve Cole. Take it away.
Okay. Let's give a hand to all our speakers who are here today. We've got a lot more information online about what NASA's doing to study the Earth. You just need to go to www.nasa.gov/Earth. We also have a special Earth Day page. That's also www.nasa.gov/Earth. Thank you all for coming. Well done.